everyone, my name is Brad Kelly, teacher and tutor with the Princeton Review, and welcome to our ongoing live stream web series on academic geometry. This week we are going to be covering interior and exterior angles of polygons. And if you're interested in some of our back catalog, we have several others on geometry topics we have done so far, on topics like the Pythagorean theorem, similar triangles, and several others. So if you just search on for the Princeton Review on YouTube and type in my name, it should come up. Second of all, this is all is a part of our brand new academic geometry class that we are offering online. I know that this year is very weird for many of you. Some of you are taking classes entirely online. For other people, you have kind of a hybrid situation. Others of you are back full time, but maybe you're in masks or things are just a bit of a mess. But either way, if you feel like you're not getting the academic support that you need in your geometry class, our class might be a great idea for you. And next thing, please feel free to write any questions that you have into the text box, but be aware it will take about 30 seconds before I actually see those questions and can answer them. So don't be surprised if there's a little bit of lag. So let's start off with some basic definitions that are going to be necessary before we even start talking about interior and exterior angles. The first one is just a polygon. So a polygon is just an enclosed figure with 3 or more sides made up of only straight lines, and no lines may cross any other lines. So this hexagon would be a good example of a polygon, all straight lines, no lines crossing any others. This oval, on the other hand, is made up entirely of a curved line, so that would not be a polygon. And this figure is either not a polygon because those lines are crossing, or is 2 polygons, specifically triangles, on top of each other. So the interior angle is just an angle formed by the intersection of 2 sides of a polygon that's entirely within the polygon itself. And an exterior angle is an angle formed between the side of a polygon and an intersecting side that has been extended. So that yellow angle right there will be an exterior angle. So if we're talking about interior angles of a triangle, many of you have run across the interior angles of a triangle, and the sum of those is always going to be 180 degrees. We can use this to figure out what the sum of the interior angles in a quadrilateral would be, because a quadrilateral could just be made by putting 2 triangles together, like so. So given that we have 2 triangles, each of which has a degree measure, sum of interior angles of 180 degrees, we would just add those up to get that the sum of the angles in a quadrilateral is 360 degrees. The other easy way to get there for quadrilaterals is in a square, you have just 4 right angles, which would add up to a total of 360 degrees. So to create a pentagon, a hexagon, an octagon, decagon, dodecagon, nonagon, whatever we want here, we can just keep on adding triangles. And for the most part, outside of triangle, quadrilateral, pentagon, hexagon, and octagon, most of the other names are not going to matter too much. They aren't going to come up very often in math. So I wouldn't really worry too much about the fact that, say, a 9-sided figure is a nonagon. So if you notice, right, this pentagon that we have just has, excuse me, it's just made up of 3 triangles, each of which has a sum of 180 degrees. So we just add those all together to get that the sum of the interior angles of a pentagon is 540 degrees. And we could do something similar with this hexagon. Or even with this, I think that's a decagon maybe? See, what is that, 10 sides? Yeah. Doesn't matter how many sides there are, it's still just made up out of triangles. So, right, for each side, we're just adding a new triangle. So the degree measure of the interior angles will just increase by 180 degrees. Which leads us to our formula for the sum of the interior angles of a polygon, which is the sum is equal to 180 times n minus 2, where n is the number of sides. So what's the sum of the interior angles of the shape above? So this would be an octagon because it's got 8 sides. So first we're just going to write out the formula. The sum is just equal to 180 times n minus 2. And then we're plugging in 8 because this is an octagon for n. And then we're just going to solve, right, to get that the sum is 180 times 6, or 1080 degrees. So that is what all of those angles in this octagon will add up to. So let's look at a slightly more interesting problem that's a little bit more similar to what you guys might be doing in class. So you might just be asked, what's the value of x here, given those other 5 angles in this hexagon? Once again, write out the formula first, 180 times n minus 2. And since this is a hexagon, n equals 6, so we're just plugging in 6 and solving to find that the sum of the interior angles of this hexagon is 720. Now we can just plug in all the angles that we have, add them up, and they have to add up to 720, right? So 720 would just equal 590 plus x, or 130, right? So just by taking that one step at a time, we can pretty easily get to this answer, as long as we remember our original formula, 180 times n minus 2. But can we find the number of sides given only the degree measure? Absolutely. We would be doing the same thing, just backwards, right? So if we were looking for what type of polygon has interior angles that add up to 1800 degrees, we would just plug in 1800, I'm sorry, for our sum in this formula to get that 1800 equals 180 times the quantity n minus 2. Then we can just divide both sides by 180 to find that 10 is n minus 2, or n is 12. So a 12-sided figure, just as a heads up, a little bit of semi-useless trivia for you, is called a dodecagon, and looks awfully close to a circle at this point. So if we are talking about regular polygons and their interior angles, so a regular polygon is just a polygon in which all of the angles and all of the sides, all of the angles are equal and all of the sides are of an equal length. Obvious examples would be squares and equilateral triangles, but for those of you in the United States, a stop sign would be a good example of a regular octagon. So since the sum of the interior angles of a triangle is 180 degrees, as we know, and we know all 3 angles are equal because this is a regular polygon, all of the angles must equal 60 degrees, right? Because it's just 180 divided by those 3 angles. And if you notice, what we did there is we just divided the interior angles, the sum of the interior angles of the polygon, by the number of sides to find the degree measure of each angle in the regular polygon. So that's just the basis of our formula for the degree measure of the interior angle of a regular polygon, which is the interior angle equals 180 times n minus 2 over n, right? Where once again, n is the number of sides. So what's the value of x in the polygon above? So we can just, in the regular polygon above, sorry, that is a very important word in that question. So first we would just want to write out the formula. The interior angle equals 180 times the quantity n minus 2 over n. So since this is a 7-sided figure, we would just plug in n equals 7. And just as a heads up, this is called a heptagon. Not that that's necessarily important information, but in case you were wondering. A lot of people mistakenly call it a septagon, but when it comes to polygons, all of them take Greek prefixes, not Latin prefixes, so it is in fact heptagon, not septagon, which sept comes from the Latin. So let's just plug in 7 and solve. So it would just equal 180 times 7 minus 2 over 7. And just as a heads up, if you didn't want to use this formula, you can just find the sum of the interior angles first, and then divide that by the number of sides at the end, if you just prefer to do it as two pieces, or if you can't actually remember the formula. It's one of those that tends to be fairly intuitive. So our interior angle here is just going to equal 900 over 7, which is about 128.57 degrees. Yeah, anytime you're dividing by 7, you get weird numbers. But wait, we can do this going the other direction too. If we're given one angle in a regular polygon, we can figure out how many sides that polygon must have. So we would just be plugging in the value of the interior angle into the formula and doing a little bit of algebra and solving for n. So how many sides does a regular polygon with interior angles measuring 144 degrees have? First, let's write out the formula. Interior angle is 180 times the quantity n minus 2 over n. Next, plug in 144 for the interior angle and just solve. So we would have 144 equals 180 times the quantity n minus 2 divided by n. So multiply both sides by n, because I hate fractions and don't want to deal with them, to get 144n equals 180n minus 360. So when we play with that algebra a little bit, 36n will equal 360, and n will equal 10, so we're looking at a decagon, which is a 10-sided figure. So let's move on to talk about exterior angles and polygons. So the sum of the exterior angles of any polygon will end up equaling 360. And remember that orange angle there would be the exterior angle, though this here would also be an exterior angle. Does not matter which direction you go. If you notice, those are actually vertical angles, so it doesn't make a difference here. So we can prove this fairly easily, that the exterior angles will add up to 360 when we're dealing with regular polygons. First, we just want to write out that equation again. 180 times n minus 2 over n equals the interior angle. And exterior and interior angles are always supplementary, which is kind of makes sense, right? If you look at it, the yellow angle and the red angle here make up a whole line, so they have to be supplementary. So that means the exterior angle would just be 180 minus that interior angle. So 180 minus 180 times the quantity n minus 2 over n. I know the algebra is starting to look a little bit hairy here, but it'll simplify in a second. Lastly, there are going to be n total exterior angles. We would not count the green and the yellow angles as both being exterior angles. Those would both be considered one. A second one would be this right here. And this right here would be a third, etc. So from there, since there are n total exterior angles in a polygon, because each interior angle only takes one exterior angle, the sum of the exterior angles would be each exterior angle multiplied by the total number of angles, which is n. So let's do some algebra here. First, let's distribute that n. And when we distribute that n, we get the fraction cancels out. So we get 180 times n minus 180 times the quantity n minus 2. And let's distribute again. To get 180n minus 180n equals 360. So those 180n's will cancel out, and we get a total sum of 360 degrees. right? So the sum of the exterior angles of a regular polygon will always be 360 degrees. We have just proved that using algebra here, and that will be true no matter how many sides we're talking about. But what about irregular polygons? Sometimes called non-regular polygons, depending on your class or even where in the world you are taking your math class. But if we are dealing with irregular or non-regular polygons, we can prove that their exterior angles will have to add up to 360 degrees. We just end up with some weird algebra involving infinite series. So each angle is supplementary to each of the interior angles. And the sum of the interior angles is 180 times n minus 2. So if we know that, we can actually prove that the exterior angles will add up to 360 degrees. So to find the sum of those exterior angles, we would just need to set up the equation below where the sum is equal to 180 degrees minus the first interior angle, right? We would be subtracting there because these are supplementary angles. And then we would add that to 180 minus A2 plus 180 minus angle 3, all the way up through 180 times, minus the nth angle. So we can rearrange this. If you notice, each term in this list of n terms is being subtracted from 180. So we have n 180s, each of which is being subtracted from an angle. So we can just kind of regroup this to say that the sum is 180 times n minus just angle 1 plus angle 2 plus angle 3 all the way up through adding angle n. But wait, that part in the parentheses is just the sum of all n interior angles, which we know is 180 times n minus 2. So we can just plug that in for a1 plus a2 plus a3, blah, 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 which would give us that the sum is 180n minus 180 times the quantity n minus 2, which is probably starting to look pretty familiar from the last slide here. So when we distribute, we get 180n minus 180n plus 360, or just 360. So the sum of the exterior angles for any polygon is 360 degrees. That's weird. In a regular polygon, the exterior angle times the number of sides will always be 360, which makes sense based on what we were talking about in the last slide. There are n exterior angles, and they always multiply together to give us 360. So if it's a regular polygon, they should all be the same, and it's just each exterior angle times n. So if you know the number of sides and one of the, you can find the degree measure of each exterior angle, or if you know one exterior angle, you can find the number of sides, right? So how many sides does a regular polygon with an exterior angle of 72 degrees have? So there are a couple of ways to solve this. You could plug 72 into the formula that we just saw on the last page, or you can find the supplementary interior angle and use the formula for the interior angle of a regular polygon, so the 180 n minus 2 over n, to solve. We're going to use the formula we just brought up because let's practice it. First, we're going to write out the formula. The exterior angle times n is 360. Then we're going to plug in 72 for the exterior angle, and we are going to solve. So 72n equals 360. So we have a pentagon here, or 5 sides, because that's what the question was asking. So what's the value of x in the regular polygon above? This might look a little bit more confusing, but there's just one extra step here. First, we're going to write out the formula. The exterior angle times n equals 360 to find the value of each exterior angle. right? So each of these exterior angles, because it's a regular polygon, will be equal. So that does mean that these two angles have to be equal because they are both exterior angles, even at a slightly different orientation here. So now we're just going to plug in 6 for n and solve. Right, so the exterior angle times 6 equals 360. So each exterior angle has a degree measure of 360. Oh, sorry, of 60. Sorry about that. And we know the sum of the interior angles of a triangle is 180. So 60 plus x equals 180. And x will equal 60, which actually means that this is going to be an equilateral triangle. Since all three sides are equal at 60 degrees, that means we're looking at an equilateral triangle. So actually, if they had given us, say, the side length of, say, this, we would also know what that side length and that side length would have to be. Lastly, let's look at the exterior angle theorem, which just states that the exterior angle of a triangle is equal to the sum of the two remote interior angles. So the remote interior angles are just the angles that are not supplementary to the exterior angle. So they're not the interior angle that is related to the exterior angle that we were looking at. It also states that the exterior angle will be greater than either of the remote interior angles, which makes sense because neither of those angles can be 0 and still have this be a polygon, right? Because if they were 0, we'd be looking at a straight line. And since they add up to that exterior angle, they will each have to be less than it. So let's see if we can prove this. And we can do this with some pretty simple algebra. We just need to know that E and X are supplementary, so add up to 180. And the sum of interior angles in a triangle is 180 degrees. So E plus X is 180, X plus Y plus Z is also 180. So E plus X then has to equal X plus Y plus Z, because both of those add up to 180. So subtract X from both sides, and we get that E equals Y plus Z. So congratulations, guys. You are now as smart as Euclid, who came up with this theorem a couple thousand years ago. But be warned, this particular theorem only applies in triangles. Some of the exterior angles being 360 applies to all polygons, not just triangles. So this is a triangle-only theorem. So let's talk about some important things that you guys should be taking away here. First off, the definitions. A polygon has to be an enclosed figure with 3 or more sides made up of straight lines. So a circle is not a polygon. And no line may intersect more than once. So like an X is not a polygon. And an interior angle is just an angle formed by the intersection of two sides of a polygon that is within the polygon itself. And the exterior angle is just going to be an angle formed between a side of the polygon and an intersecting side that has been extended, as we just saw. Next, the sum of the interior angles of any polygon is just 180 times n minus 2, where n is the number of sides. The interior angle of a regular polygon is just going to be equal to the interior angle equals 180 times n minus 2 over n. And this will be true for any angle in that polygon. Since it's a regular polygon, all of those angles will be equal. So the sum of the exterior angles of a polygon always equals 360 degrees. And the exterior angles of a regular polygon are related to the number of sides by the formula exterior angle times n equals 360. And lastly, the exterior angle theorem states that the exterior angle of a triangle is equal to the sum of the two remote interior angles. It also states that the angle, exterior angle will be greater than either of the remote interior angles, right? So the remote interior angles, remember, are the ones that are not supplementary to the exterior angle in question. And that only applies to triangles. All right, so at this point, I'll open it up to some questions. I'm happy to answer any questions that you may have, no matter how tangentially related to what we're talking about. And beyond that, thank you for coming. We're going to meet again in 2 weeks when I believe we talk about cones and pyramids. Oh, looks like we might have a question coming in. All right, so no questions at the moment, but feel free to ask any questions that you do have. And thank you all for coming.